And I'm going to do kind of a short video on this one because this is a very important concept. It's okay to leave it by itself. Um, I've got another checklist. You're going to find over the years I've learned to just when something's really important to make kind of a checklist or a step-by-step process. I'm going to move my picture here out of the way so you can see what it says. Writing a first law equation. How do I write a first law equation? Well, that's a pretty straightforward process, but if nobody sits down and talks to you about it, it can seem magic. And if you're just following along with AI, used to, I would say, if you're just copying Chegg solutions or some other online services, you lose the subtlety of how to do this. And honestly, for me, when I'm testing students in an exam, this is the skill that I'm testing you for. This is literally one of our course outcome objectives is to be able to simplify the first law for any kind of system I put in front of you. So this is the process through which I want you to go through and do that. Writing a first law equation. Step one, and again, I'm going to write it here, but you can see it on my notes here on my PowerPoint slides. Um, Step one is draw your system. Those of you that have had statics, this is kind of like drawing your free body diagram. And sometimes I see rookie instructors will say things like, "Oh, that's simple. You can do it in your head." Okay, no, a PhD with 20 years of experience might be able to do it in their head. Maybe a really, really, really sharp student, maybe it'll do it in their head. It doesn't mean everybody can. Draw your system. I promise you, this makes the whole process so much easier. It doesn't have to be pretty. It doesn't have to be detailed. Just draw a blob and that represents your system, and that's okay. Something that's got a boundary, draw it, because what's really important, the most important thing here is we need to be able to draw energies crossing the boundary, right? And I relate this back to a free body diagram because it's kind of the same thing there. You're going to draw all the forces acting on that object. And then when you apply Newton's laws to it, it makes it real easy to add up those forces. It's the same thing here. Draw the energies crossing the boundary, and those can be three things. That's either heat, work, and or mass. And so what it does is it forces us to really think about, okay, what are the things in my equation? I only draw them if they're actually there. I'm only going to draw heat if I'm actually going to account for heat. Maybe I'm going to draw heat in, I'm going to neglect the heat out because basically I'm looking for the net heat in. Maybe I'm going to draw work in, going to neglect the work out because I only see one thing applying a force here. Um, what I've done in step two represents now the left-hand side of my equation, right? On left hand of my equal sign, I'm going to add the ends and subtract the outs. All the energies I've drawn in step two, now I'm going to add the ends, I'm going to subtract the outs. And then this becomes step four, lets me then finish up my equation. On the right hand side of the equal, right hand of the equal sign, um, we're gonna write energies that change. And that's going to be U. It's going to be kinetic energy. That's going to be potential energy. And a lot of times we're going to be working with a stationary system where the kinetic energy and the potential energy are going to be negligible. That's point 4b down here. Kinetic and potential energy are only going to be present if the entire system changes. The internal energy, we're going to approximate based off of other properties that I know. So if it's water in R134, we're just going to go to property tables. We'll talk a little bit more in the next few videos about what do we do with ideal gases and then later solids and liquids. But this is the process through which, and I've kind of written it in, kind of by hand here. This is the process that we'll use to write a first law equation. I'm going to draw my system. I'm going to draw all the energies, heat, work, and mass that I think are present crossing the boundary. Then I'm going to start writing my equation. Step 3 and 4 is where I write my equation. The left-hand side is going to be, I'm going to add all the energies coming in. I'm going to subtract all the energies going out. And then the right-hand side of the equal sign, I'm going to write any energies that are changing. It's almost always for a thermodynamics class, it's almost always going to be an internal energy value. Maybe I've got potential, maybe I've got kinetic energy. Most of the time, we're going to neglect those. Even if the boundary of the system is moving, the whole system itself is not moving most of the time. Now, in chapter 2, this is kind of what we stuck with because these two are what we stuck with because that's what you knew from a physics 1 class. Now we're introducing these. We've given you some tools to find U's for water in R134. We're going to add more tools to find U values and delta U as we move along. Okay. All right. I'm going to stop this one here because the next video, then we're going to look at an example where we actually put this into practice. All right. So this is where we'll pick up next time.